This is Tim. Say hi, Tim. Today we'll be following Tim on his adventure in 5G as an enabling technology for building smart pods. 5G is the fifth generation of cellular network technology. In 2019, 5G was launched in several countries around the world, such as the United States, United Kingdom, South Korea, Switzerland, and more. It is slated to go in widespread commercial development in 2020 and will coexist with 4G for at least the next decade as older devices get phased out. The main benefit of 5G over 4G is that it allows a theoretical peak download speed of up to 20 gigabits per second, which is about 50 times faster than 4G LTE. It has end-to-end latency as low as 1 millisecond to support ultra-reliable low-latency communications, while 4G has an average latency of 50 milliseconds. It supports massive machine-type communications to connect a large number of IoT devices while being power efficient. And it also supports more frequency bands such as millimeter waves, massive MIMO, 3D beamforming, and network slicing. The global economy is supported by ports, as they are responsible for up to 90% of goods being transported all over the world. With rising demands on logistics and an ever-increasing need for operations to be sustainable, it is only with the advent of 5G that will allow smart pods to come into being. But what makes 5G so important to the success and backbone for building smart pods? Let's go through some of the features of 5G that are useful for building smart pods. First, 5G is similar to 4G in that it uses packet switching to deliver packets over an IP network. In packet switching, a message is broken down into many parts called packets, which will then be sent through a link and reassembled at the destination. Voice services are also supported through the use of VoIP, thereby improving the utilization of the network resources while supporting more users simultaneously. Packet switching is more efficient than circuit switching as it allows a link to be shared by many users without the need to reserve bandwidth. Packets can be rerouted dynamically in case of a busy link or a link failure. It is connectionless, as a connection does not have to be established first before transmitting data. Circuit switching was last used in 3G networks. It is inefficient as it is connection-oriented. A path between the sender and receiver must be established first. The established path cannot be shared by other users as long as it is active. The drawback of packet switching is that it introduces queuing delay and packet loss, which is apparent with 4G. Queuing delay is the time spent by the packet sitting in a queue waiting to be transmitted onto the link. Packet loss is the failure of one or more transmitted packets to arrive at their destination. In 4G networks, these drawbacks can result in undesirable effects such as: in data, packet loss produces errors. In video conference environments, it can create jitter. In pure audio communications such as VoIP, it can cause jitter and frequent gaps in received speech. In the worst cases, packet loss can cause severe mutilation of received data, broken up images, unintelligible speech, or even the complete absence of a received signal. 5G aims to solve these problems by increasing bandwidth capacity and reducing latency, which helps to reduce the traffic intensity. This means that more packets can be transmitted at any given time before significant congestion occurs. As smart pods become increasingly automated through the use of real-time video monitoring systems, remote crane control systems, and container transporting systems, the bandwidth requirements will also increase. 5G is able to meet the demands of smart pods, which require low latency and high bandwidth to operate smoothly. To further enhance the operation of smart pod, our solution is to print QR code on all sides of the containers so that it is possible for autonomous vehicles to automatically identify and transport containers through the use of artificial intelligence and computer vision. This will streamline the inventory management of the pod and reduce the chance of errors, thereby improving the efficiency of the pod. Network slicing is another feature of 5G that enables the multiplexing of virtualized and independent logical networks on the same physical network infrastructure. Each network slice is isolated end-to-end for quality of service provisioning. For instance, the network can be sliced into several segments such as video monitoring, which requires high bandwidth, remote crane control systems, and VoIP services, which require low latency and high reliability. IoT sensors, which are latency tolerant and require long battery life, and web browsing. Since the slices are isolated, one segment cannot overwhelm the other slices by taking too much resources. Hence, congestion can be avoided for important services. This is needed to ensure that the various systems on the pod can continue to operate without significant interruptions. Furthermore, it allows a more granular level of access control, as each slice can be managed independently. This is an important feature which ensures that only authorized staff are allowed to access critical services which may contain sensitive business information. Security is also improved, as any cyber attacks on a slice will not affect the other slices. To overcome the limited coverage of mmWave spectrum, 5G will rely on highly dense deployment of low-powered small cells that cover small geographic areas. Besides that, massive MIMO is also used to increase the bandwidth capacity by employing large antenna arrays at the base stations so that a large number of users can be served simultaneously. 3D beamforming is used to focus the signal at a certain angle, which increases the coverage distance. Since the signal is more concentrated, interference is also reduced. Another feature of 5G is device-to-device communication, which is similar to peer-to-peer architecture, as devices can communicate with each other directly without a central server. In peer-to-peer architecture, devices act as both the receiver and sender. As there is no need for a central server, costs can be reduced. It is also highly scalable, as new peers can provide service to other peers. Our solution is for 5G beacons to be placed on ships so that ships can communicate with other ships without the need of a base station. As devices have a direct connection with each other, latency can also be further reduced. Some possible implementations include an intelligent transport system, which can enhance the automation of ships by transmitting proximity location, weather information, and sea condition to determine the most efficient and safest route. Furthermore, multi-hop device-to-device paths can be used to extend the coverage of the network. This is especially useful when there are ships that are just out of range of the smart pod's base station range. The ships that are nearer to the pod can act as a relay to ships that are out of range. Thus, the smart pod can manage and coordinate the traffic flow of the ships more efficiently. Some of the challenges to implement 5G are its relatively low coverage, which in turn requires many small cells to be installed. Furthermore, 5G is not fully wireless as one may think. In order to support the tremendous bandwidth required by 5G, it is important to have sufficient fiber backbone to support it. That's all from us. If you have any questions or thoughts, feel free to leave them in the comment sections below, and we'll try our best to answer them. Thanks for watching.